Welcome to the Economist in Your Ear podcast. What if the clearest sign of life beyond Earth has just been found? A tantalizing whisper from another world. But we find ourselves in a frustrating predicament. We can't actually get to it to confirm. We love exploring stories that truly challenge our understanding, pushing the boundaries of what we thought possible. And this one, involving a fascinating Martian rock sample, is absolutely buzzing with scientific intrigue and, well, real-world implications. It's got scientists excited, sure, but also a bit frustrated, highlighting how even the biggest scientific breakthroughs often hinge not just on brilliant minds and cutting-edge tech, but also on budgets, international cooperation, and maybe even geopolitics. Today, we're taking a look at a situation that really brings all these elements into sharp focus.
Indeed. And we're going to meticulously unpack the recent findings from NASA's Perseverance rover and its latest compelling discovery on Mars. We'll explore why this particular find is being cautiously called a potential biosignature, what that classification truly signifies, in the rigorous world of astrobiology, and critically examine some of the significant challenges and assumptions that surround the monumental task of bringing these precious samples back to Earth for the definitive answers we all crave. It's really a journey into Martian geology, planetary science, and frankly, the complex reality of space exploration.
Okay, let's unpack this fascinating development then. The Perseverance team, they've been incredibly busy drilling cores in the Jezero crater, that location believed to be an ancient lake bed. And they've hit pay dirt, so to speak. Specifically, they found something pretty remarkable in a mudstone, affectionately nicknamed Chayava Falls, that's nestled within the broader Bright Angel Formation. And for those of you following these missions closely, it's Bright Angel, not Bright Trail, a detail our sources were careful to point out.
Right, precision matters here.
Absolutely. And the core sample itself, which they've dubbed Sapphire Canyon, that's where things become truly captivating. It reveals these striking, dark, leopard spot halos and dots embedded within the rock. These aren't just random imperfections. They seem really crucial to the story. So what makes these specific spots, these unique patterns, so incredibly significant? Why all the buzz?
Well, what's truly compelling here is the precise mineralogical and chemical context of these spots. They coincide with the presence of specific minerals like vivianite and greigite. Now, these aren't just obscure minerals. They're key indicators of localized reduction reactions.
Reduction reactions. Okay, remind us.
Right. So to put it simply for our listeners, these were a fundamental type of chemical process where compounds gain electrons.
Yeah.
On Earth, particularly in organic-rich muds or sediments, this kind of patchy, localized redox chemistry where compounds are constantly gaining and losing electrons is very often a telltale sign of microbial metabolisms.
Oh.
It's what happens when microbes breathe or process chemical compounds, often in the absence of oxygen. And the mudstone itself is fine-grained, which is important because fine-grained sediments are excellent at preserving delicate microtextures and organic molecules.
Good preservation potential.
Exactly. And yes, it does contain organic molecules, those complex carbon, hydrogen, nitrogen compounds that are, the fundamental building blocks of life, although their presence alone doesn't always definitively mean life. But the combination, the context, that's what makes it so intriguing.
So if I'm getting this right, these aren't just some accidental splotches. They point to very specific chemical processes happening in a way that here on Earth often signals biological activity. But Joel Hirowitz and his team, they're excited, I assume, but they're being incredibly cautious, aren't they, about making any definitive claims?
Oh, absolutely. Their caution is, well, it's a hallmark of good science, really. While these textures and this particular chemistry are remarkably consistent with biological activity, we absolutely must acknowledge that abiotic or non-biological pathways could potentially mimic them.
Abiotic mimicry. Okay.
For instance, certain geochemical reactions could create similar redox gradients or mineral formations. Although it's worth noting, many known abiotic processes that produce these specific minerals typically require higher temperatures than the rock seems to have experienced.
That's interesting. Lower temperature points, maybe more towards biology.
Potentially, yes, or at least it makes some abiotic explanations less likely. But the crucial challenge lies in discriminating between biotic and abiotic origins. And the rover instruments, as advanced as they are, well, they simply lack the precision for a definitive answer.
Right.
We need Earth-based laboratories. Labs equipped with nanoscale analytical techniques, ultra-sensitive isotopic analyses, high-resolution crystallographic studies, things you just can't miniaturize onto a rover. And this immediately raises a fundamental question for us. How do we truly prove the presence or absence of ancient life or its biosignatures from such incredibly subtle clues when we're limited to remote analysis?
Yeah, this does sound familiar, doesn't it? This isn't the first time we've seen headlines or heard whispers about potential signs of life on Mars. I definitely remember, and many listeners probably do too, the huge buzz around the ALH 84001 meteorite back in 1996. Can you remind us about that story and maybe more importantly, the lessons learned?
That's an excellent point to bring up, yes. A really crucial historical precedent. The ALH 88401 meteorite, which came from Mars, landed in Antarctica. It generated massive excitement. Huge. Scientists at the time claimed they'd found what looked like microfossils, tiny worm-like structures, plus specific minerals and organic molecules. Collectively, they interpreted this as evidence of ancient Martian life. The news was enormous. Even President Clinton commented.
Boy, I remember that.
But as often happens in science, decades of intense debate and much more detailed research followed, and eventually abiotic explanations emerged for all of its initially tantalizing features.
All of them. Wow.
Pretty much. The microfossils could be mineral formations, the magnetite crystals, formed by non-biological processes, the organics, maybe non-biological sources, maybe even contamination from Earth after it landed. So the cautionary lesson from that episode is profoundly important for today's discussion. Extraordinary claims require extraordinary evidence. To truly satisfy what's known as the null criterion for proving ancient life, you need multiple, mutually reinforcing lines of evidence. Things like specific isotopic signatures, unique molecular structures, patterns that are incredibly difficult, if not impossible, to explain through any known abiotic process.
So the null criterion, basically saying evidence has to be not just consistent with biology, but pretty much inexplicable without it. That sets an incredibly high bar.
Precisely. It encourages critical thinking, demands that level of scientific rigor. You have to exhaust all the non-biological explanations first. And this history, this criterion, it's vital. It helps us approach Sapphire Canyon with both, the appropriate scientific excitement for its potential, but also the necessary rigor and, frankly, healthy skepticism. We know the journey from potential biosignature to confirmed life is long and very demanding.
And to even begin that journey properly for Sapphire Canyon, our sources, including that compelling analysis in The Economist, they emphasize one absolutely critical point. You must get these samples back to Earth. The kind of super advanced instruments needed to clear that null criterion hurdle, they just don't fit on a rover millions of miles away.
On that point, The Economist is absolutely right. The limitations of doing this remotely are just fundamental. Specialized instruments for techniques like nanoscale, secondary ion mass spectrometry, or SIMS, that lets you analyze isotopic composition at a microscopic level. Atom probe tomography, mapping atoms in 3D. Clumped isotope geochemistry, looking for temperature-dependent bonding patterns that can indicate biological processing. These aren't just fancy names. They're tools to scrutinize samples at almost an atomic level, finding those subtle isotopic ratios or structures that could be biological fingerprints.
Indispensable tools, it sounds like.
Completely. And of course, returning potentially bio-bearing samples also demands incredibly rigorous planetary protection protocols. You can't risk contaminating Earth. Plus, you need a high-containment sample receiving facility. That's exceptionally complex and naturally very, very expensive to build and operate.
Okay, but here's where we need to maybe dig a bit deeper than that article. The Economist claimed quite definitively that America has no way of doing so, referring to getting samples back. That sounds pretty final.
Yeah, and when we connect this to the broader picture from our supplementary materials, that statement might be, well, a bit too strong, perhaps overstating the finality of the situation. While it's certainly true that NASA did scrap the original Mars sample return, or MSR, architecture, that was the one heading towards maybe $11 billion and a return date way out in 2040.
Which caused quite an uproar.
Understandably, but it's inaccurate to say there's now no way. NASA is actively, and I'd say aggressively, re-architecting the mission. They're looking for cheaper, faster, more efficient options. We're already seeing exciting proposals coming from industry partners. Lockheed Martin, for example, has put forward a concept they claim could be under $3 billion.
Wow, that's a big difference.
Huge difference. And Rocket Lab suggests maybe sub $4 billion with a potentially much earlier return date. So the situation is far from dead. It's much better described as being in flux.
Okay, in flux, not dead. That's a key distinction.
Definitely. The final outcome isn't set, and of course Congress still holds the purse strings. So the future of MSR is still a very dynamic and, yes, politically charged landscape.
That makes sense.
Yeah.
What about the idea sometimes floated, like in the Martian film, of international collaboration? Could China help out? with these Perseverance samples? Is that realistic?
Ah, the Martian scenario. It's a compelling idea, isn't it? That spirit of global scientific unity makes for great cinema. However, in reality, direct NASA CNSA, that's the Chinese National Space Administration cooperation, is legally very constrained by something called the U.S. Wolf
The
Amendment.
Wolf Amendment, right?
Yeah, this legislation significantly restricts NASA from engaging in bilateral activities with China without specific congressional and FBI approvals. And those approvals are rarely granted for sensitive space missions like this.
So unlikely for these specific samples.
Highly improbable for a joint retrieval of Perseverance's samples, yes. Meanwhile, China is forging ahead with its own really ambitious space program. Their Tianwen-3 mission aims to launch around 2028 and return samples by 2031, which is incredibly impressive, potentially beating NASA back. But critically, these would be samples collected from its own landing site, not from Perseverance's carefully cached tubes in Jezero Crater. So even if China's mission is a huge success, it wouldn't directly answer the specific questions posed by Sapphire Canyon, unless there was some unprecedented, legally cleared joint effort, which, again, seems unlikely right now.
So geopolitics really does play a role here.
Absolutely. It highlights how deeply geopolitics influences the pace, the direction, even the fragmentation of scientific progress on these big shared questions. Okay, so let's try to synthesize the scientific evidence for a moment. Let's summarize the strength of this biosignature-like signal from Sapphire Canyon. On the pro side, the case for potential biological involvement is bolstered by several factors. First, you've got the right kind of sedimentary context, a former lake bed, prime real estate for ancient life, if it existed.
Right, Blended.
Second, the fine grain size of the mudstone, ideal for preserving delicate microtextures and organic material over billions of years.
Good preservation.
Third, that combination of organic molecules with those specific redox minerals, like vivianite and greigite. That's compelling, especially because, as we said, they aren't easily made at low temperatures abiotically. And finally, those distinct spatial patterns, the leopard spots, they're consistent with something called diagenetic hotspots.
Diagenetic hotspots.
Yeah, these are basically localized areas within a rock where chemical changes happen after the initial sediment deposition, often driven by things like fluid flow or, crucially, potentially by microbial activity creating its own little chemical environment.
Okay, that sounds like quite a few intriguing pieces lining up. But as we keep saying, science isn't simple. There must be counter-arguments, alternative explanations, right? The cons.
Precisely. It's suggestive, definitely, but it's absolutely not definitive yet. So on the con side, we have to acknowledge the known abiotic routes that could potentially mimic these observations.
Yeah.
For example, organic molecules don't have to come from life. They can originate from meteoritic infall, just space dust raining down over billions of years.
Right, non-biological organics.
Exactly. And those redox halos, they can also be formed by just fluid rock chemistry. Imagine subsurface water, rich in minerals, interacting with the rock in a patchy way. That could create localized chemical reactions that look very similar to microbial activity, but without any biology involved.
Like chemical patterns forming naturally.
Yes, groundwater flowing through tiny cracks could cause oxidation here, reduction there, making patterns that might fool you. And as we've hammered home, the rover instruments, for all their cleverness, they just lack the decisive isotopic and nanostructural discrimination needed. They can tell us what's there, but not always how it got there, with the certainty needed for a life claim.
Got it.
So while it's undoubtedly biosignature-like, it's not yet and cannot be remotely a confirmed biosignature, not without getting those samples back.
This is truly a tantalizing moment in space exploration then. So what does this all mean for us, the listeners, waiting for an answer to that huge question? Was there life on Mars? What should we and scientists be watching for in the coming months and years? What are the next steps?
Okay, several critical developments will shape this narrative going forward. First, keep an eye out for lab reproduction studies here on Earth. Can scientists, in controlled lab settings, recreate these exact mineral organic textures and patterns at low temperatures without biology?
The abiotic mimicry test.
Exactly. If they can do it easily, the biological case for Sapphire Canyon weakens. If they struggle or fail, it strengthens the biological possibilities significantly. Second, keep a very close eye on policy and budgets, especially in Washington. Will Congress restore or reshape MSR funding? Will they embrace one of these newer, leaner industry proposals? Which one gets the green light? That determines the whole sample return timeline.
The political and financial angle.
Crucial. Third, watch China's Tianwen-3 mission closely. its milestones, its sample collection success, and any potential for international transparency about what they find, even if it's from a different site. Its success impacts the whole landscape. And finally, perseverance itself. Is it finding more mudstones like this in other parts of Jezero? And critically, how secure are both the samples cached on board the rover and the backup depot at Three Forks? Those samples need to survive for a future pickup.
Right, protecting the treasure chest. What a complex web of science, engineering, global politics, everything. This Sapphire Canyon find feels like the most suggestive chemical textural hint yet from Mars, like you said. A tantalizing whisper, not quite a shout, but one that really demands our attention. The economist, as we noted, is right on the money that Earth labs are decisive, and that, frustratingly, politics and budgets might delay that ultimate proof for years, maybe even decades.
And that's where that critical interpretation comes in, looking beyond just the headlines. While the article correctly identified the need for Earth labs, we saw it maybe slightly misidentified the rock formation.
Bright angel, not bright trail.
Right. And perhaps overstated the U.S. return capability as being totally dead. As we discussed, influx seems much more accurate. New, potentially cheaper, faster architectures are actively being considered. Meanwhile, yes, China is racing ahead on its own parallel independent path. So ultimately, whether Sapphire Canyon ever definitively answers the question of ancient Martian life, right now it hinges less on the fascinating geology of Mars itself and more on the programmatics of human space exploration, the political will back here, and the geopolitics playing out on Earth. It really invites you, the listener, to consider how deeply interconnected our grand scientific ambitions are with our sometimes messy societal and political realities, and how those earthly concerns can either propel us forward or hold us back in this incredible quest.
A fascinating and maybe slightly sobering conclusion to ponder. A lot for us all to keep an eye on. Thanks for listening. Follow us for daily insights into world affairs, and don't forget to like, comment, and share.